for
chemistry.
Yeah, baby. Yeah.
Hello. Yeah, I'm going through alcohols today. If I can work out what I'm actually doing. Oh my days, what am I doing? What's going on here? Oh my god, glasses on. Right, what is happening now? Okay, hi up, hi there. Going through the reactions of alcohols. I know some people wanted to go over pH of like weak acids and stuff. Um, so I might do that next week. Um, yeah. So I thought, well, I'll go through some alcohols. So these are just some of the things you got to know for AS and A2 to do with alcohols. So how you guys doing? E-wave. What's E-wave? Hope everybody's doing good. Cool. Okay, starting off, let's get into the alcohols business. Yeah, I need to sort out my background at some point, so it's actually all covered up. Waving about, aha, got you. Right, yeah, I'm a bit slow on the uptake. What are three different types of alcohols? So you might have studied alcohols, you might not. Hopefully you know the functional group of alcohols. And there are three different main types of alcohol. So if you've got your functional group of alcohol, of course, it's going to draw ethanol. Functional group is the OH group. Make sure if you are asked to draw the display formula, you draw the bond between the O and the H. If you don't, you won't get the marks. So that would be ethanol. And what's funky about alcohols? Well, they come in three flavors, which is primary, secondary, and tertiary alcohols. So you need to know about those, primary, secondary, and tertiary. What's the difference essentially? Let's have a little look. Hopefully we've got them. Hold on. There we go. So you got an alcohol here, and you can see we have primary alcohols. Now primary alcohols have to have they have one R group attached to the OH. So what is an R group? Does everybody know what an R group is? Does everyone know what an R group is? So an R group is like methyl, ethyl, propyl, butyl, pentyl. You know, it's a carbon hydrogen side chain. So a primary alcohol, sometimes shown in notes, when people are doing shorthand, when you're making your notes shorthand and you want to write down primary alcohols, just put a 1 with a little circle. So primary alcohols, that's the symbol. Secondary alcohols have to have two alkyl groups. So we can see that they've got one R group here. So this is an R group, and they've got another R group here. Now that could be a methyl group. These could all be hydrogen, or that could be an ethyl group. So what do I mean by that? Well, it doesn't really matter. This could be another carbon like that. So that would be ethyl there. That's an R group. And then this would be methyl. So that's like butan 2-ol is a secondary alcohol. But that means you've still got to have an H attached. So primary has one R group, secondary has two R groups. So this is one of the, oh my days, what is that? And that is, ay. Let's get rid of those. That's just getting uglier and uglier. You get the point. And the tertiary has no hydrogens attached to this carbon atom. And the tertiary, we can put a little symbol 3 with a circle. So it's got 3 R groups around it. Okay. Now that massively affects the reactions of the alcohol. So knowing whether being able to spot a primary, secondary, or tertiary alcohol is super important. Hi, well done. Nice. All right, guys. So make sure you can identify primary, secondary, tertiary alcohols, and we'll have a go at that. That will come up. So I want to whiz through the content and then do exam questions, essentially. Do you know what I mean? It's only a kind of simple topic. he says. Properties of alcohols. So what are the boiling points like compared to alkanes of roughly the same size? So where the carbon chain is the same size. So if you think about it, let's check out ethane. Here is ethane. Ethane is an alkane. Of course, what is going to be the difference between the boiling point of ethane and ethanol? What do you think the main differences are and why? So that's ethane. Let's check out, that must be a little biofuel plant that's making ethanol over here. So let's do ethanol, as that's the alcohol with 2 carbons in it. What would you say are the factors that give ethanol a higher boiling point than ethane? Anyone got a clue why ethanol has a higher boiling point? While you painfully watch me draw out this. So if you compare these two, why has ethanol got a higher boiling point? Yes. We're not breaking any of the bonds when we're boiling them. James, we're not breaking any of the bonds when we're boiling them, but the bonds do come into it. So we have hydrogen bonding here. So between 2 ethanol molecules, so if I have another ethanol molecule next to this one, they're going to delta positive hydrogen is going to hydrogen bond to the delta negative oxygen. I could draw that out, but you guys would have the pain of me doing that. It doesn't just have hydrogen bonding. What other types of bonding, what are the 3 intermolecular forces you think this ethanol molecule will have? So if I was to draw, oh my days, let's not draw another one. That's just too painful to watch me draw another one. Just use your brain to visualize another ethanol molecule next to it. Okay. What kind of bonding can they have? Of course, they can have hydrogen bonding, which is going to be like that between, you know, on another ethanol molecule. You're going to get that going on. So there's another ethanol. That is some hydrogen bonding. Hydrogen bonding is the strongest of the intermolecular forces. You're going to need to use a lot of energy to break that. But guess what? There's van der Waals forces as well. Thank you, Important 45. Thank you, James. We've got VW forces as well. So don't forget that you're overcoming van der Waals and within those van der Waals forces, you've got the temporary dipole, and you've got permanent dipole, because you've got the carbon and the oxygen. That is a permanent dipole there as well. So you're going to get dipole forces, and you're going to get hydrogen bonding. So you've got both. Now this little guy over here, it's just got London whatever dispersion forces, induced dipole. So it's just got van der Waals. And which of these would have the stronger van der Waals? So we've established that ethanol or alcohols have van der Waals and hydrogen bonding. Would an alkane, would ethane or ethanol have stronger van der Waals? So van der Waals comes down to you working out the MR essentially, and you should be able to just take a quick glance and go, right, that's 24 plus 6, 30, whatever that is, 46 for ethanol, and we've only got 24, 30 for that. So ethanol, so if I was writing an answer to explain why ethanol has a higher boiling point than ethane, I'd want to say it has hydrogen bonding, whereas ethane only has van der Waals, and ethanol is larger, so the van der Waals forces it has are stronger, as it has a greater electron cloud, whatever, more electrons. So yeah, cool. So we've established that. Now what happens as they get bigger, the alcohols? So we go to butanol. Can't really see that here, it's all looking a bit down here in the mud. It's looking a bit dirty, and I can't even get my bonds to go in the right place. So I'm not going to draw that whole thing out, but you can just visualize in your head butanol is going to be bigger. So there's less hydrogen bonding for the size of the molecule, but the van der Waals forces are increasing. The hydrogen bonding, okay, it's still just got one OH group, but the van der Waals forces are increasing. So we would expect alcohols, as we increase the chain length, for their boiling points to increase. Of course, branching on any organic molecule reduces, disrupts those van der Waals forces, and so branching, if you have 2 and one's straight and one's branched, the branching brings the boiling point down a bit. But generally, as they get bigger, the boiling points are going to go up. So that should be straightforward. Higher boiling points as we get bigger. Now, looking at the solubility, Looking at the solubility, again, alcohols, the small alcohols like ethanol are soluble. Why are small alcohols soluble and big alcohols not soluble? So there's a little difference between the boiling points here. Small alcohols dissolve, big alcohols don't, or are less and less soluble the bigger they get. Same kind of thing, we got hydrogen bonding between the water molecule. But now if I have a carbon chain with 20 carbon atoms in it and 20 hydrogen, so if I have a big fat carbon chain, little alcohol group at the end, that fat carbon chain is going to come into contact with the water, and it cannot hydrogen bond to water. So what you're asking the water molecules to do with a big alcohol, you're asking the water molecules to give up their hydrogen bond to an existing water molecule and swap it with a van der Waals interaction with the carbon chain of an alcohol, and they're not likely to do that. So alcohols become less soluble the bigger they get. They'd rather retain their hydrogen bonding with the other water molecules around them than break that and try and bond to the carbon part of a alcohol. Whereas here, the ethanol is very soluble because the water is just like, look, it's kind of like equal energy. If I bond to this, or if I bond to another water, the hydrogen on another water, or if I bond to the hydrogen on the alcohol, it's about it's just as good for it. So there we go. Right. Yeah. So with branching, why does it reduce boiling points? The molecules can't get as close, so those forces are weaker, basically. So it affects, it disrupts the van der Waals forces between the molecules, and they can't, like, so if you look at like having long straight chains, when you look at like big polymers like cellulose and stuff, they're straight chained, not branch. Why? Because it wants to give strength to the cell wall of plants, and it can form those strong intermolecular forces. So you don't want branches, they disrupt the intermolecular forces. So cool. Right, what do we want to do here? Yeah. You should actually make notes on some stuff that you need to make notes on at some point, because all the stuff I talk about gets tested on, and we'll go over some questions in a second. Right, the formation of alcohol. So what reactions do you need to know for the formation of alcohols? We can hydrate alkenes. So you guys know steam effect, steam effect. Woo! Yeah, you guys might have done this in GCSE triple. If you take ethene and you add steam to it, it forms ethanol. Does anyone know the three reaction conditions? You might have done this at GCSE as well, depending if you did IG. Some of you might have done IGCSE. Depends really. You got to know the three reaction conditions. Maybe I can't remember if it's in triple AQA, but this is the molecular formula for ethanol. C2H5OH. Anyone know the three reaction conditions? And you also have to know like the pluses and minuses of making alcohol this way. The alcohol, when you go to wash your hands and you use, during COVID, everyone was using those gels and stuff, and the hand sprays everywhere, sanitizers. Those kind of alcohols are normally made from industrial methods. And lots of other alcohols in industry and chemistry are made with industrial methods. And the reason why this method is favored is because it makes purer alcohol. So the product produced has a higher level of purity than the other method. So you do need to know that. That's exactly important 45. The H plus, so it's one of the conditions. What do you think the H plus stands for? Sorry, just slurping coffee away. Acid catalyst, absolutement. Well done, acid catalyst. So what we want to say here, what type of acid? Well, we're going to go with phosphoric. So phosphoric acid is the preferred catalyst. The temperature, oh my god, I have to remember these myself. And there are and 60 atmospheres. So if you don't know that, that's the type of thing you want to put on a revision card. It's something you have to know off by heart for chemistry A level. Is it going to make or break your exam? No, but it's likely you're going to get a 1 marker testing you on one of those. So there we go. Yeah, I mean, I don't see why you couldn't use conch. I should put conch sulfuric acid, phosphoric acid as well. Is it conch? It is conch, isn't it? Yeah. Now, phosphoric acid and concentrate and sulfuric acid in organic chemistry can be pretty much interchangeably swapped. There is a slight difference. Phosphoric acid is a slightly nicer catalyst. You don't get so many side reactions. If you use sulfuric acid to, you get more side reactions formed. So sulfuric acid has a tendency, um, yeah, to get you more side reactions essentially. So yeah, it's not as clean. You don't get as clean a product. So potentially they will favour phosphoric acid. I have to look at the spec whether you can use sulfuric acid. There's no reason why you can't make. You're only taking the hydrogen ions from it. So yeah, you could have sulfuric acid. I have to check your specific spec to see if they allow it, but they should do, in my opinion. Oh, I didn't really say why the downsides about this. Before I move on to fermentation, which is the second way to make alcohol, what are the upsides and downsides? Well, what's the problem with using an alkene like ethene to make alcohol? Where does ethene come from? Where does ethene come from? No, the base catalyst for this, you don't want a base because you need a hydrogen. So you want those hydrogen ions. Where do you think we get ethene from? Oh, it would be helpful if I don't lose the chat. Yeah, crude oil, nice one. No, ethene, yeah, crude. No, you're right, but ethene we have to get from crude oil cracking. You don't get it directly from crude oil. You've got to do fractional distillation of the crude oil and then crack the crude oil where you make the small alkenes. So straight away, it's a finite resource. We're using up a non-renewable resource like crude oil. Okay, limited supply on the earth, etc., etc. You get the idea. Okay, so that's one of the downsides. Obviously, you could say, oh, it needs 300 degrees. Where do you get 300 degrees from? Well, you have to burn something or you have to use energy. So you might use renewable energy resources to heat something up, but you got to use energy regardless. And then you need, it's not massively high pressure, but a little bit of pressure. So it's a little bit more expensive, this method. Let's look at the cheaper method. But the upside, the big upside to this method is it makes pure alcohol. You can use sulfuric acid, concentrated sulfuric acid or phosphoric acid for this. But again, most of the examples recommend phosphoric acid for this one, but of course you could use concentrated sulfuric acid. I think beyond the specification, there's some problems sometimes with with alkenes and what do you call it, sulfuric acid with some side products that are a little bit. Sulfuric acid can form like carbon dioxide, sulfur dioxide, and some other sorts of side products. Okay, that's absolutely right. High temperature, high pressure, you wouldn't want to say necessarily dangerous, but expensive because yeah, high pressure you need big containers to keep it all in, and then a high pressure 60 atmospheres isn't that high, but you do need thick walls. What did we say? High temperature 300 degrees isn't that high. Again, I would at A level I would argue more that it's a little bit more expensive because of those reaction conditions and the catalyst. Okay, fermentation. This is the cheaper method and the kind of greener method, hence the lovely fields here. And of course, this is not this is a production plant where they're making biofuel, which is basically bioethanol, essentially. And the lovely thing about this is, of course, photosynthesis. So these plants are producing glucose, and then all we've got to do is use a certain living organism to turn the glucose that these plants make into alcohol. What organism do we use here for fermentation, guys? Anybody remember the organism used for fermentation? So, and we're going to use yeast, and yeast type of single cell fungi, and you're going to do this about 30 degrees. You don't want to denature the enzymes of the yeast, so you've got to do it at a lower temperature. Also, when it produces ethanol, at a certain percentage, like once it gets to more than 15% ethanol in your product solution, that level of ethanol will kill the yeast and kill your reaction dead. So you've kind of got to make it in batches rather than a continuous process. With the hydration of steam, you can just do it continuously, keep adding in reactants. With this, at some point, all the yeast are going to die, so then you've got to turn it off and take that alcohol away. Now, when they're making drinking alcohol for leisure and pleasure for drinking alcohol, this is the method they use. And obviously, if you want to make the stronger alcohols greater than 15%, you need to take them to a distillery and distill them. But we also use alcohol in biofuels. And why have I got photosynthesis there and fermentation and then combustion? Because the argument is that using alcohol, ethanol, to be burnt as a fuel, if it's made from fermentation, it's carbon neutral. We can check out why it's carbon neutral. You remember this equation from GCSE. This is the photosynthesis equation. Have a look. It takes in 6 carbon dioxides. So to make my glucose, we took away 6 carbon dioxides from the air. And then during fermentation, that glucose was turned into 2 ethanol molecules and released 2 of the CO2s that were taken in during photosynthesis. Now I take that and I fill that ethanol into my car. If you're in Brazil, they use alcohol in the cars like biofuels. So you're going to combust that with oxygen. So yes, alcohols can combust. It's a kind of form of oxidation combustion, and they react with the ethanol there, and you're making 4 carbon dioxide. So if you add up the carbon dioxide released by both fermentation and by combustion, it equals the amount they took in from photosynthesis. So essentially, it's not contributing to global warming is the argument. So that's the advantage of this one. Whereas with the other one, you had to take the fossil fuel, you had to do fractional distillation to get ethene, which involves energy, heating, lots of energy use. You had to then take that limited finite resource and you had to hydrate it with steam. Again, you needed temperature, and again you needed a higher pressure and all of that sort of stuff. But the advantage is it makes purer product. This is going to have loads of dead yeast. It's going to make you the alcohol. Carbon dioxide's not a problem. That's a gas that can escape. But it's going to have dead yeast floating in it because yeast are our catalyst for this reaction. So you've then got to like filter it or do whatever you want to do before you stick it in a car engine. Yeah, so carbon neutral. Carbon neutral means carbon neutral means that the amount of carbon dioxide taken in at the start of the process is equal to the carbon dioxide taken out, so it doesn't have a carbon footprint. So essentially, if you fill your car with this ethanol and you drive around burning that and releasing the carbon dioxide from the back, you're kind of not contributing to global warming, because when that ethanol was made by the people who make it in their big farm, it took in the carbon dioxide. So it's kind of a green fuel is the idea. Okay, so 6 carbon dioxides go in, and it's renewable. We can just plant more plants. We're not going to run out of plants. We can just chuck more seeds down and grow more plants. We can burn as many as we like, and those plants, in their lifetime, they will have taken in the same carbon dioxide that was released when the production of alcohol and the burning of the alcohol took place. Okay, of course, the disadvantage, as I said before, it's not pure, the ethanol. And so you're going to have to do distillation, which might use some energy and stuff. So there are some other arguments to say, is it truly carbon neutral? Because I've got to gather all these plants up, and then I might have to transport the ethanol to not petrol stations, but car filling stations or whatever. So no process is truly carbon neutral because you're not taking into account all of that business. But here are some questions comparing those two processes. See if you can do these ones, guys. Oh, is it vegan? Uh, yeah, I don't think vegans count microorganisms. Yeah, they don't because they eat corn and stuff like that, so they don't count yeast. So it's like a vegan process potentially. No animals are harmed in that process, just plants and microorganisms. Although there is an argument, but you don't really need to know about at A level, but there is an argument that the use of biofuels, this lovely field I have as a background, could have been used to make houses for young people, or it could have been used. That food is being turned, that sugar, that carbon is being turned into fuel to burn in cars rather than food to feed people. You might say, so what? If everyone's got enough food, how does that matter? Well, if the farmer wasn't growing fuel, he or she would be growing food, and that would mean there's a bigger supply of food and it would lower the cost of food. So in some weird way, some people argue the use of biofuels causes food prices to go up because farmers decide I'm going to sell this stuff I'm going to use this food to make alcohol for cars, and therefore there's less of that food in the supply chain, so the cost of the food goes up. Yeah, you can kind of keep arguing about for everything with these things. Right, first question, people going D, 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 D. Well done. The first question is D. First answer is D, yes. You're right. Now, if you've done KC, sounds like you guys might have done KC. An increase in pressure increases the value of KC. Hopefully you know that pressure and concentration have no effect on KC. So actually, which statement is not correct? Yeah, that's a false statement because KC is only affected by temperature, not concentration or pressure. And pressure is you'd kind of normally use with KP. Yeah, well done, well done, well done. You've done, Casey. You're absolutely right. Right, question 2. Got the first people. Oh, some people said B. James going A. Brass boy B. So let's check it out. Which statement is correct? So is truthful about the production and the use of ethanol as a biofuel. I've got an ulcer in my mouth at the moment. If I'm talking like this, then that explains why. A biofuel. So let's check out A. Let's go through them. A biofuel, ethanol, is produced by the fermentation of glucose in the presence of yeast and air. There's a mistake here which I didn't highlight on the last slide. So why is A wrong? A is wrong. There's one incorrect bit. Most of the sentence is correct. What's the incorrect part of statement A? Hopefully you can spot it. It's the air. It's actually an anaerobic process, and being a bit of an idiot, I didn't remind you of that. If you go back here, there's no plus oxygen in fermentation. This is an anaerobic process. Process. Okay. B. Yes, it's purified by fractional distillation. I did sort of waffle about that a little bit. Yeah. Afterwards, it has to be purified. No carbon dioxide is released when biofuel ethanol is burned. No, that is incorrect. Of course, carbon dioxide is released. Bioethanol burns with a cleaner flame than ethanol. No, it doesn't burn with a cleaner flame. So, yeah. What about the last one, guys? Yeah, the air is wrong there, but it doesn't matter whether they put oxygen or air. Both would be wrong. You actually need, when you make alcohol, you can make alcohol at home in your house. All you need is a sugar. So the basic, simplest form of making alcohol is sugar and buy yeast. Make a solution, put it in a plastic tub. I wouldn't recommend you do this because you'll make yourself very sick, but if you put sugar in a plastic tub and you pour water into the sugar and you added yeast, which you can buy from the baking section, and you sealed it so there's no air in there, then the yeast will turn the sugar into alcohol. but you'll probably create a poisonous, impure brew that will make you very sick. So, because you need sterile conditions, but lots of people make wine and make beer and make alcohol at home. But yeah, you need anaerobic conditions. Otherwise, the yeast is going to aerobically respire and not make ethanol, produce carbon dioxide and water. Yeah, well, I wouldn't. Yeah, I wouldn't recommend doing it myself. I wouldn't trust myself to make alcohol at home, so I wouldn't expect that would be a sensible thing. But they sell all the. They used to sell all the equipment in Homebase and in Sainsbury's. They probably still do at certain times of the year. Right, in the UK, the industrial ethanol is now produced. You're not. It's actually illegal to make alcohol at home and then sell it. I believe that's illegal. So, but not illegal to make it at home and drink it or whatever. Bathe in it, whatever suits your fancy. In the UK, industrial ethanol is now produced by the direct hydration of ethene. This process has largely replaced the fermentation method. What is the reason? Direct hydration. Yeah, it does use a catalyst. Look, I didn't really explain, but that is, or didn't obviously explain very well, that is the acid catalyst. So it does use an acid catalyst. It uses phosphoric acid. This is the direct hydration route. And so the answer is A. It's purer. So you just really need to concentrate on hydration makes purer ethanol. It doesn't use milder conditions because it uses 300 degrees and 60 atmos. Produces ethanol by slower. It's not slower. Higher temperature. It's faster. Fermentation, cheaper process. Hydration, more expensive. Fermentation, like anyone can do. You can do it at home. Hydration, you can't be doing 60 atmospheres and 300 degrees at home, so you can't do that at home. Right, let's move on. Oh, see if you can get this one right. Ooh, tired today. Which statement about the industrial production of ethanol from ethene at 300 degrees is correct? So we have, that's ethene plus water, reversible symbol, alcohol. Oh, they've made that exothermic. It is. Lovely. Good to know. The use of an acid catalyst increases the yield of ethanol. So does a catalyst affect yield? What does a catalyst do? The reaction is slower than fermentation. It's done at 300 degrees, so I doubt it's going to be slower. Fermentation's about 30 degrees. So let's go with that one's incorrect. As temperature, an increase in temperature at a constant pressure increases the value of Kp. Oh my good gosh. You going D? An increase in pressure at constant temperature increases the equilibrium yield. If we increase the pressure, it's going to go to the side. That's got two gas molecules, one gas molecules. It will shift to the side with the least gas molecules. Yeah, that's correct. Now, if you wanted me, the use of an acid catalyst, catalysts do not affect the equilibrium position, so do not improve your yield. They only increase the rate of reaction. They'll increase the speed with which you reach equilibrium, okay, or decrease the time taken to reach equilibrium. Now, an increase in temperature at constant pressure increases the value of Kp. You might not have done Kp yet, but just to explain that one in case you wanted to know, Kp, exactly the same as Kc. You use smooth brackets, but essentially it's products over reactants. So if we increase the temperature, we're going to increase the product over the increase. Oh my god, what are we doing here? I don't even know what we're doing here. What are we doing here? An increase. Yeah, anyway, it's D. I'm going to try and explain that, and I'm probably going to mess that up, so. Okay, let's move on. My head's not working. So alcohols can be dehydrated back to alkenes. Oh yeah, I did. I did. Don't worry about that. Skip that one. Ah, yeah. Probably. Okay, alcohol, let me go through dehydration of alkenes. Alcohols can be dehydrated back to alkenes. What is the HS? Okay, that's just asking you. This is a catalyst, so we can spin them back to ethene. Now, this has implications of making ethene from alcohol. Let's say we make our alcohol. What am I banging on about? Okay, if we get our alcohol by fermentation, right, then it's a green process. And therefore, if our alcohol has come from fermentation, technically we can make alkenes from alcohol from a renewable resource. So, the whole idea that we can only get alkenes from crude oil, actually, potentially, we can get ethene, which is an alkene, and can make polyethylene, which you make plastic bags, your Sainsbury's or Tesco's bag out of. We can get those from by dehydrating alcohol. So there's like a green implication there, which is decent. Don't ask me why I put a picture up of someone who is thirsty, I guess. Haha, they're dehydrated. Right, so what happens here? You have to know this reaction. So do I want to bother going through it? Yeah, go on then, let's go through it. Right, so this is going to be an elimination reaction. We're going to wipe out a whole water molecule. We're going to eliminate a water molecule, so an H2O. So let me show you how that's done rather than draw it out. Where does the alcohol come from? Oh, so the alcohol comes from photosynthesis to make glucose. And then you can do the yeast, use the yeast in anaerobic conditions to turn your glucose into ethanol. So there's been a little bit of carbon dioxide release, but not as much as was taken in. Remember, they're carbon neutral. The plant took in 6 CO2, and then you make 2 ethanol molecules for that 1 glucose, and it releases like some carbon dioxide, but not as much as it took in. So you've now got your ethanol, which has been made in a green way without producing carbon dioxide, and you can now turn your ethanol into an alkene. That's just something, yeah, they don't often ask about that, but let's have a look at how we dehydrate an alcohol into an alkene. This is something that comes up in core practicals for many of the topics, many of the exam boards. So this all looks a bit confusing. This is a reaction mechanism you have to know about. So what we've got here, this is the catalyst. So you can take this from sulfuric acid or phosphoric acid. Your oxygen always has a lone pair there. Remember, it's actually got 2 lone pairs. It's got 2, right? Water molecules have 2 as well. Oxygen has 2 lone pairs, but we're only interested in one of them. So we're just going to show this one. As the hydrogen ion from the catalyst approaches the alcohol, the electrons, a pair of electrons or lone pair of electrons, form a covalent bond with a hydrogen ion. Hydrogen ion has no electrons and it wants 2 in that 1s2 orbital. Its 1s orbital is empty and it wants to fill it. So it takes those, it grabs those from the oxygen. The problem is, this then makes what's called an oxonium ion. Whenever oxygen has 3 bonds in organic chemistry, you have to put a plus charge on it. And that is an unstable ion and won't hang around long. Now, this is a weird bit in A-level chemistry that you only really get here. You don't get this in many of the other reactions, but because oxygen is more electronegative than carbon, it pulls the pair of electrons towards it, and that is represented by this orange arrow. That is the pair of electrons in the bond getting pulled towards it. Once they get close enough, that pair of electrons leave the bond and go to stabilize the oxonium ion. They get rid of that plus, and our water breaks off. Problem is, those two electrons have gone and they've left this positive, okay? This has been essentially protonated. So this is now a carbocation. That water molecule has been eliminated, so we've got elimination. And then what's happened is this bond here donates it, the hydrogen donates its pair of electrons to stabilize that. Now it can't be one of these hydrogens because that would leave this still positive. So it has to be one of the hydrogen atoms on the carbon atom attached to the carbon that had the OH. It's all getting a bit long, isn't it? But one of the hydrogens that's attached to the carbon atom, that's attached to the carbon with the OH, or adjacent to the carbon with the OH, donates its electrons there. Now, it could have been this hydrogen, could have been this hydrogen. Any one of these three could donate their electrons there and form ethene, the double bond there. So we end up with a water molecule released, and then in the very final step, we regenerate the catalyst. And this is why we say the sulfuric acid remains unchanged. It might go, or the phosphoric acid, whatever acid you're using, remains unchanged. So it goes down to, it goes from H2SO4 to HSO4 minus, and then it reforms H2SO4 at the end when this hydrogen ion joins on. That's right, you always get the catalyst back. The catalyst reforms right at the end. Now, one of the important bits, we're going to do some multiple choice questions, is, I don't even know if they ask it in those, but in the harder multiple choice questions in A2, they ask you about, like, can this alcohol form, or can this one not form? And it's to do with where the double bond forms. So if you look back here, it's always a carbon atom attached to the carbon with the OH that donates its electrons to form the double bond. So the double bond will always come off the carbon with the OH on it. All right, let's have a little look at an example where you can have multiple products. So here we have butan 2-ol. What do you think are the two possible? There's three isomers of this. Anyone got an idea what the three isomers of this are going to be? Can you think of the three different alkenes? They're all going to be isomers. They're going to have the same molecular formula, but different arrangement in space, business, all of that. So we've got three isomers here. Anybody got an idea of the three isomers we can make? Well, not of butan 2-ol, I mean, sorry, of the alkenes that are made. So what's going to happen is this water molecule is going to be eliminated. And also, so that water molecule is going to be eliminated. What with? With a hydrogen from this. So essentially what happens is a hydrogen from this comes down here and acts as our electrophile, and the lone pair of the electrons on that go there, and the upshot is that this is going to break off, right, and leave that as a carbocation essentially. I mean, it takes a little bit of time. You've got that weird arrow thing that I showed you earlier. I'm not going to redraw all of that, but essentially that all breaks off, and then the options are any one of these hydrogens here can join, or any one of these hydrogens here can sacrifice themselves to make that double bond. So it's always got, this one here can't. This one over here cannot make a double bond because it's not adjacent, so it can't lend its electrons all the way around there. Oh, good. I think you guys have come up with but2-ene and but1-ene. Nice. Good. Now, let's get a bit deeper on but2-ene. So you might go, well, how does, let me just show you, oh my days. Oh my gosh. It's better just leave it in the chat rather than me type it out. So we've got butene and butene, very good. And you might be struggling with the third one. You might say, is it 2-methyl-propene? You might be thinking, or the only problem is we can't go to methyl because that would be, you have to like break things off and change them around. What can happen is this hydrogen can go there and make butene, and this hydrogen can go here and go butene. Now let's look at butene. What can you get from butene? Have a look at butene and tell me, what are you thinking now could be two different isomers of butene? Yeah, they have to have a double bond. Yeah, they've all got a double bond, butene and butene. Yeah, absolutely important. We can get EZ. So look, so there are three possible, when you dehydrate larger alcohols, larger than 3, so once you go to bute, pent, hex, you have the problem that you're going to get either butene or butene, and then if you get butene, you could get this, which would be Z, or you could get E, where, you know, I put one hydrogen up there and we put one hydrogen there, so you've got like that, which would be Z. That would be E, antigen, sorry. Yeah, so EZ. So yeah, they do have to have a double bond, and that's what these guys are doing here. They're donating. So you can always just work it out like that. Let's move on. So, oh, that's showing it for us. Look, that's a bit nicer than my crappy drawing. There's butene, and there's butene. But of course, this is antigen because the hydrogen's there, methyl group. You fold that methyl group, that'd be CH3 up there and CH3 up there. So if you're wondering, if you're not getting the EZ thing, it's because this is exactly what they've drawn there is exactly the same as drawing that, right? So that's butene. Obviously, that is E butene, but then we could have Z butene and Z butene. It doesn't matter which way, but you have two identical groups either side of the double bond like that. Okay, so we got Z, we got we got E. I keep calling them the wrong names. E means opposite, Z means sisters or something. Cool. Okay. Nice. Okay, have a go at these two. Quick challenge. So yeah, have a go at these.
Say when.
Round 1.
Let's go. Okay, yeah, I think round 1 was a little while ago, but there we go. Which alcohol forms a mixture of alkenes when dehydrated? So that kind of lends to what we've just been talking about. Which of these can form a mixture of alkenes? I've got 2 Ds. Double D. Any other answers? I think you could be right. Yeah, that was quick. That was quick. Okay, I don't know why I played that twice. That's not good. Okay, yeah, you're absolutely right. Let's have a look at C. Some people might be going, why not C? Why not prop? So just for those of you that are like, why the F can prop not do 2? Well, look, if prop 1 ol there, right, this is this one here. This can only form prop-2ene because it's the hydrogen here or here that has to donate to form that. Obviously that would be gone, so that can only ever form prop-2ene. Propan-2ol, the second one, like that, can only ever, the double bond is either going to, yeah, the double bond is going to form either prop-1 or prop-1. So both of those are going to be prop-1ene. So pentan-1ol, same thing. Pentan-1ol, it's at one end. It can only form one version. Pentan-2ol has enough that it can form different versions. So you can get like pent 1-ol, pent 2-ol, etc. Cool. Okay, yeah, D, 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 D. What about this one? Which compound can be dehydrated? Oh, that should be easy, this one. What about this one? I think the second one's nice and easy. It's basically, if you get this, you're saving yourself time. Which one of these can become an alkene? Has anyone got mocks at the moment, or got their exams coming up, or is everyone all good? Yeah, yeah, yeah. You all got it. The answer's C. Well done. Boom. There you go. Smashed it. Okay. Yeah, mocks is. When are your mocks? Important. Are you in year 2 or year 1?
I can't handle the stress no more, dog. These damn A levels.
Yeah. Are you in year 1 or 2? Year 2. Yeah. Ooh, jeez, that's nasty, man. This is a hard year, so good luck. Good luck. Um. Okay. Cyclohexanol, cyclohexene. This is a core practical. Very good chance of getting one of these questions in your actual exam on this particular one, because it's very often linked to a core practical that is A-level chemistry core practical, no matter the exam board you're doing, which is the dehydration of alcohols. They love the old cyclohexanol to cyclohexene, okay? And they tend to use phosphoric acid. Of course, they could use sulfuric acid. Of course, they could do a mixture of phosphoric and sulfuric acid. So you can use both. You're just getting those hydrogen ions. And there is actually, yeah, you can. It's the same mechanism as we looked at up here. So you've got the same mechanism going on. Just because it's a cyclo, nothing funky happens. It's the same exact thing. But we've got some A or B at A level. What, in chemistry? Oh, it's disgusting. It's foul. You're looking at like 82, 83% for an A, and normally, I mean, some years it's even higher, but about 90%, 91% for an A star. Some years it's even higher, but it's like 93% for an A star, depending on the year. Yeah, which is just like sick making. Chemistry is so hard because of the grade boundaries. I'm going to be honest, you just got so little wiggle room. Like, I've had some really, really good students that are A star all the way through, and they don't always get A's, A stars. They sometimes drop down to A's, and it's just there's just so little wiggle room. You've got to remember the type of students that take chemistry all across the country. Who are you up against? That's what you have to ask yourself. Who's your competition? And so don't beat yourself up with A-level chemistry, because your competition, the reason the grade boundaries are so high is because your competition is all the people that are taking chemistry. Visualize the type of students in every school, private schools, all the schools that are picking chemistry. You haven't got anyone sitting there going, oh, I don't know what to do for A-levels. Oh, F it, I'll take chemistry. No one's doing that, right? People are going, oh, F it, I'll do drama, or oh, screw it, I'll do an art A-level, or oh, screw it, I'll do psychology. I'm not putting those A-levels down, they're all good. But the fact is, the people that take chemistry, half of them are trying to get into medicine. So those people, so you're up against the cream. That's why that boundary is so high, because you've got all these mad people getting 100%. Yeah, but that's what I'm saying. It's not your fault. It's the fault of all those people that are just crazy insane, and they're like, I will sacrifice my life to get an A, or they're just like bzz, bzz, bzz. So you're up against all of those. Now, if you picked yourself a nice little A level where people, notice the reason why biology has a lower grade boundary. Like, let's be honest, biology is not as hard as chemistry. There's no, like, conceptually, there's a few difficult skills in bio. I'm not saying bio is easy. You've got to memorize a whole heap of stuff, but at the end of the day, there's a lot of people who pick bio who are like, yeah, I'm doing music, I'm doing psychology, and I'm doing bio, right? I'd rather be up against that person than up against the person who's like, I'm doing maths, further maths, physics, chemistry, and biology. That person is the person you're up against in chemistry. Same as physics, which is why you're in trouble. Okay, now, yeah, so it's like doing further maths or something. If you're doing further maths, I guess the grade boundary is just disgusting because there's only... You haven't got anyone just like chilling out in further maths. Right, so there are 3 stages to making an alkene. The first stage you can see here. This is where you get your cyclohexanol and you put your acids, it could be phosphoric or concentrated sulfuric, and you put them in a round bottom flask. Do you know the name of this process? What's going on here? This is called distillation. So what we're going to do, sometimes they drip the alcohol down into here from above, and they heat the acid from the bottom and they drip down the alcohol in there, whatever. But essentially we're going to distill off the hexanol. Now how do they do that? The hexene, sorry, we want the hexene coming off, not the hexanol. So we do 83 degrees. Sometimes you put anti-bumping granules. You don't always have to put anti-bumping granules in. You're not heating vigorously, so you don't really need anti-bumping granules in this one. I don't know why I put that there. And you just need to make sure you know the arrows, the directions. So, what's going on here? Right, you're making cyclohexene. You're bound to have some cyclohexanol left in there, right? It's going to be impure. Now, cyclohexanol has a higher boiling point than alkenes. Why? The hydrogen bonding. So it might be linked to that question we did earlier about boiling points. The alcohols have hydrogen bonding and van der Waals forces. They're going to have higher boiling points than the cyclohexene. This is great because it means if I maintain this at 83 degrees, which is the boiling point roughly of cyclohexene, then I'm going to be evaporating mostly cyclohexene, and the cyclohexanol, which maybe boils at a higher, I don't know what it is, 96 degrees, something like that, say, isn't going to be coming off like massively. Now, does that mean that none of it's going to evaporate? No, of course. Like water will evaporate at room temperature. Evaporation happens at any temperature. So we're not going to just get pure cyclohexene down here. We are going to get a little bit of evaporated cyclohexanol, unreacted cyclohexanol in there. And we may get some impurities from the reaction in there as well. A couple of things you could be tested on. You might be asked, yes, this is really important, 45. You have to know that in distillation, distillation's the one where it's on the side like this, okay? I'll show you reflux in a sec. Distillation is like this. It has to be tilted downwards because we want our condensate, we want our stuff that's condensed to roll down, our impure product, and go there. We don't want it rolling up, otherwise it's going to roll back. So that's always diagonally down. Now why when you're doing distillation? The answer's the same for reflux and distillation, but the arrows look a bit different. So the water must come in here. It's going to go around here. And this is very important because this comes up. If you do AQA, they love to ask this question about the arrows. What this does is this ensures you're always going against gravity. So the way to do it is my water in must go against gravity. And then if you say that, right, it's going to go uphill. It maximizes the filling, ensures that the whole thing is filled with water. And what that does is that maximizes energy transfer between the water and the hot vapor. I know what you're saying. I get your point. Like, hold on, isn't it better for the cold water to come in here where the vapor first comes in, so it hits with cold water? The problem if the cold water comes in here, it doesn't push up and completely fill the container. It just goes like that bit. So the hot vapor is not getting cooled in the first stretch. Just comes in like that. It's not really getting cooled because gravity's pulling the water down. So you want to go up against gravity and push right to the end here, and so that the entire cylinder is cold. And that's the argument. So how do you put that in words? You just want to say to ensure that the Liebig condenser is completely filled with cold water and to maximize energy transfer between the vapor and the water to make sure that all of it condenses. Maximize energy transfer efficiency, blah, blah, blah. Anywho, Then we get this here. By the way, why do we not use a naked flame? Why no naked flame here? And they love to ask that question. That is like they're addicted to ask. They love to ask that question at some point in your exam with this practical. But with the reflux, the arrow is going to look slightly different, but it's the same answer. So the answer is always to completely fill the Liebig condenser, or to completely fill it, and to ensure maximum energy transfer to the to remove as much heat as quickly as possible, or most efficient energy transfer, because you want to make the condense it as quickly as possible. Yeah, you get uneven heating, vigorous. What products have we got here? We got alcohol in there. And we got alkene, but it's the alcohol we're more bothered about. The alcohol is flammable. So the vapors that are coming out of the round, but you might seal it, but you're still going to have some vapors in the air from your cyclohexanol. They're going to catch alight. So whenever we're doing organic chemistry, we want to use a water bath, not a naked flame. And you just want to say organic compounds. They're often flammable. So there we go. The vapor, volatile and flammable. Okay. Stage 2 is the separation. Okay, now the vigorous stuff, you have the anti-bumping granules for that, and mainly that's for reflux. Stage 2 is known as separation. So, oh gosh, that's hanging off the page. Never mind. Right. What do we do here? I'll just talk you through what we're doing here, peeps. So, once your product comes out here, over here, you transfer it to what's called a separating funnel. What does this look like? It looks like a burette. You could use a burette. Okay, you could use a burette. It's basically a version of a burette. It's not quite as long as that, because that would be murder to use. But you could technically use it. It's similar. So you've got this separating funnel. And what you're going to do is you're going to add water. You put this in the separating funnel, and then you add water. Now, anything that dissolves in water is going to form an aqueous layer. And your stuff that doesn't dissolve in water, that doesn't form hydrogen bonds, what doesn't form hydrogen bonds? Cyclohexene. It's non-polar. There's no delta positive, delta negative bit, so it's not really very soluble at all. That's going to be in this layer. So all of our soluble things, like our cyclohexanol is not that soluble, but yeah, cyclohexanol, maybe a bit of, or any other aqueous things, any ions, any organic things, any bits of the acid will be in any excess acid. So maybe any of this phosphoric acid, that's going to be soluble. That's all going to be in the aqueous layer. So now we can tap that off, run that down, get rid of anything that's aqueous impurities, and we're just left with the organic layer and maybe some organic impurities. I don't know if that's too big to actually be soluble, or if that is still soluble. It's got hydrogen bonding, but it's just got this big fat carbon chain that maybe water doesn't want to bond to. I'd have to look it up. Anywho, so we've got our organic layer. And so what you do with the organic layer, you tip it up and pour it out this way. You've got rid of the aqueous layer, then you pour the organic layer out that way. That contains your product, your cyclohexene, and you pour that out. Why do you pour it out from the top? You don't want it to run through past where it's all covered in aqueous stuff. So anywho, right. And then the third stage, again, it's not going to be totally pure, but the third stage, you're going to, I guess cyclohexanol has gone with the aqueous because of the OH bonding, it's soluble. So the third stage is just called drying, and you add anhydrous calcium chloride. There's various other things you can add. They're drying agents, and they will soak up any moisture that's in there, any water that's left behind. And then sometimes they say distill it again just to make it even purer. What's the stopper for? Where's the old stopper? Ah, the separating funnel. Yeah, you've got to know that for AQA. It's in AS and A2. Yeah. So, the stopper, when you're doing distillation, you want a stopper. Let me see, have I got a reflux thing going on? Yeah, I have actually. All right, let me go through and then, anyway, I thought I'd throw that in there. I'm just going to do the oxidation of alcohols, and then we'll have a look at the reflux thing. Okay, so primary alcohols can be oxidized to aldehydes and then carboxylic acid. Secondary alcohols can go to ketones, and tertiary can't be oxidized at all. So what do you need to know? You need to know, if you don't know that stuff, put it on a revision cards, is what I would say. Let's zing. So, I get to talk about it here a little bit. So, your primary alcohol, this R group, so this is methanol, but that R group could be another CH3, so that'd be ethanol, or it could be C2H5, so that would be propanol. So you've got your primary alcohol. This is an oxidizing agent. The oxidizing agent of choice is potassium dichromate, okay, which is orange and goes green, or is it green and then goes orange? I can never remember the order. But you've got potassium dichromate, okay, and it is an oxidizing agent. It's well, yeah, oxidizes the alcohol to aldehyde. Now, if you don't distill it, you're going to get, now the chances are you're mostly going to get aldehyde, but if some of these aldehyde molecules bump into the oxidizing agent, what's going to happen? If the aldehyde molecules bump into the oxidizing agent, then you're going to maybe get some carboxylic acid. So, which is further oxidization, okay? So it can be oxidized once to aldehyde, and then the aldehyde can be oxidized to carboxylic acid. Now, if I just want aldehyde, I have to do distillation, and that means I can tap off the aldehyde. Say if I'm making ethanol from ethanol, then I'm worried about getting ethanoic acid. I can distill the ethanol off using a Liebig condenser, like we had in the previous thing. If I want to not have ethanol and I want it to go all the way to carboxylic acid, then you're going to do reflux. What reflux does is it says, look, I'm going to evaporate any ethanol that's formed, send it up here, condense it, and drop it back in with my oxidizing agent. And it's just going to keep going up and round and reacting until everything has formed carboxylic acid. So you're going to heat vigorously under reflux. Now with reflux, remember I said with your taps, with water in and water out, always go against gravity, go up. So the water's coming in and going up, and the answer is the same. Maximize to make sure that the Liebig condenser completely fills with water and to maximize heat transfer. Essentially, you want your cold water as well here, so it comes up here, it hits the biggest energy change here, and it condenses into vapor. We don't want our vapor coming out here. This is open. So your stopper is left open at the top. Why is it open at the top? The stopper is open at the top because we don't want pressure to build up. If pressure builds up, could have an explosion. So what we want to do is leave that open. You might say, but won't some of the fumes, won't some of our product, our carboxylic acid, boil and evaporate? Hopefully, if the reflux is working well, it will all condense before it gets that high, and it will drop back down and just keep reacting, okay? So you do need to know that, and you use anti-bumping granules. Anti-bumping granules basically break large bubbles into smaller ones, and yeah, they make the heating more smooth or consistent. Oh my days. Anywho, let's zing on. Secondary alcohols will oxidize to ketones. So again, you could reflux, but they only go to ketones. Secondary alcohols will only go to ketones, and tertiary alcohols can't be oxidized, okay? You can burn them, so that's a form of oxidizing. You could burn a tertiary alcohol. It's made of carbon and hydrogen. It will combust and form carbon dioxide and water, but you're not making an aldehyde or a ketone out of it. These are kind of really not in this topic. This is kind of more, but if you wanted to test, if you were like saying, well, do I have a primary, secondary, or tertiary? You could get a 6 marker. How do you know if this is a primary, secondary, or tertiary alcohol? Well, first off, try and oxidize it with potassium dichromate. So you might have an unknown bottle X of a colorless liquid. Is it primary, secondary, or tertiary alcohol? Well, you could try to oxidize it, right, with potassium dichromate. If it stays orange, it's a tertiary. If you know it's an alcohol to start with, if it stays orange, it's tertiary. If it goes green, then it's either it's been oxidized, so it could be a primary or secondary. And then what you do is you take some of your product and you react it and do the Tollens reagent or failings. And basically, failings and the Tollens test will only work with aldehydes, and that would tell you you had a primary alcohol to start with. Anywho, that's a bit long. Right, let's just do some questions to wrap up. So, alcohol can be oxidized. Which compound cannot be produced by oxidation of this alcohol? Okay, so yeah. Okay, so what this is asking you is what we need to do is work out, is this a secondary, is it a primary, or is it a tertiary? So we go, that is 1, 2, 3, that's propanol, isn't it? So that's propanol. So what we want to do is say, if I oxidize propan-1-ol, what can't I make through oxidation? What's that? That's propanal. So that's propanal. Look, that's an aldehyde. Yeah, I can make an aldehyde. So that's not the right answer because I can make one of them. What's that? Oh, that is carboxylic acid. I can make a carboxylic acid. Yeah, I can't make a ketone. How would I get the double bond O here? Remember, ketones are in the middle. I'm not picking that up, moving it over there. Yeah, we can't make the ketone. You're absolutely right. You might say, but sir, oh shit, what the hell? You might say, how can we do that? How can we make carbon dioxide? Simple, burn it in oxygen, right? If you burn something with carbon and hydrogen in, it's going to react to make water and carbon dioxide, isn't it? So, yeah. And that is a form of oxidation. They're just being a bit, using semantics there. They're being a bit cheeky. Yeah, you can make carbon dioxide through combustion. Well, let's check the next one. Yeah, B was the correct answer. Well done, well done. What is the correct equation for the oxidation of phenyl ethanol? 1-phenyl ethanol. Oh my good gosh. Okay, so again, you want to draw this out, so I'm going to do you a favor, and here is the here's the big issue with this question. All right, does anyone know what a phenol is? A phenol is a benzene ring when it's the side man. All right, when it's the side chain. That doesn't show up. Let's not use that. Well, better off if I was on a blank page rather than having a stupid picture in the way. Okay, so hopefully that's not on my head, but oh my gosh, what is that? It's like a witch's hat. It's like Halloween. Yeah, phenol's the ring, the benzene ring. Okay, so it's specifically a benzene ring. I don't know what carbon 1 is. I'm just going to go like, right, I'm coming off here. Now, I'm going to show you two that people will mash this up with and mash this up. So, some people would say, is that phenol 1, what did they call it? 1-phenyl ethanol, right? Or is it this? Which one of these is the correct formula for 1-phenyl ethanol? Oh, nice one, Gala. No problem. Take care. I'm nearly wrapping up. Now, when you look at this one here, guys, that numbering system, the alcohol is more important than the phenol. The moment they're saying phenol, it's a side group. It's not so important. So that 1 is actually telling you where the phenol comes off of. So the phenol comes off carbon 1 on the alcohol. Carbon 1 on the alcohol is the 1 with the OH group on. So this is the correct structure for phenyl ethanol. That is not phenyl ethanol, like that's not 1-phenyl ethanol, right? Because that is connected to the second carbon of the alcohol, not the first. So now we know the structure is, this is the incorrect structure. We can get rid of that and we can focus down on this one, and hopefully you guys can answer this question. So based on that, what is the correct equation for the oxidation of 1-phenyl ethanol? Oxygen represents the oxidizing agent. So what is that a secondary or is that a primary alcohol? What kind of alcohol is that? Oh, sugar. My face is over one of them. Oh no, don't worry. The one you can't see is the incorrect one. Yeah, you got it. You got it. Yeah. Yeah, it's secondary. Well done. That's a secondary alcohol because this counts as an R group and that counts as an R group, and it'll have one H there. So it's a secondary alcohol. So we have to make the ketone. And you can see there, that's an aldehyde. So that's an aldehyde. That's a carboxylic acid. They all come from primaries. So the only one that can come from a secondary is this one, which is the ketone. Yeah, you're right. D. Whew. Also notice when you want to make a carboxylic acid, you need 2 of the oxygens because you're adding an extra oxygen. Right, which statement is not correct for primary and secondary? Okay, I'm going to finish up in a minute, just got another couple of questions and then I'm done. Okay. So are primary and secondary easily oxidized to carboxylic acids by potassium dichromate? Primary, I wouldn't say it's easy. You need to do vigorous heat under reflux. So I'm going to go no. And secondary can't be oxidized to carboxylic acids. They go to ketones. They can be formed from bromoalkanes by hydrolysis. They form esters with carboxylic acids. They show hydrogen bonding in the liquid state. Is not correct. Oh, hold on. Which one is not correct? Oh, it's A. Sorry, sugar. No, A is not correct. I was going around and looking for the correct one. All of those are correct. So yeah, A is not correct. Oh, I didn't spot that. That is a bad one if you missed that. Yeah, so A is the not correct. Yeah, because they all show hydrogen bonding in the liquid state. They all form esters with carboxylic acid. So, yes, right. So it's actually A. I don't know why I went through and crossed it out. I didn't read the question properly. It asked me what one's not correct. Well, secondary alcohols can't become carboxylic acid, so A is definitely not correct. Okay, let's do the last couple. Ugh, why have I got 1-phenoethanol again? I didn't want to look at that. Didn't we just do this one? We just did this one. Sorry, folks. I swear we just did this one. It's going to be C. I think we did this. So it's the ketone. Okay, because it's a secondary, so it has to form that. And that's an alcohol, so that's not that. But that's an aldehyde. And oh, yeah. Yeah, it's ethanol. That's propanol. Whatever. I don't even know what that is. Yeah. It's going to form the ketone. Oh, that's an alcohol. Yeah. Sorry. Yeah. Okay. Waffling. Which compound can be oxidized to form this? Again, what I would do here is I draw this out and hopefully I leave myself enough space to draw this here. Kind of looks a bit dead. How do you draw these out? You're going to go like that. You're going to go like that. Ah! So that's CH3 they can't be connected to each other, so they're connected to this here. I'm not drawing all the hydrogens, just ones that might be relevant. And then you've got the carbonyl there. Oh, it's a ketone. Right, ketone. What are we looking for, folks? Now we know we've got ketone. We're looking for a secondary alcohol. Ketones have to come from a secondary alcohol. So which one of these can make a secondary alcohol? Yeah, I think you're absolutely right, Important 45. I think you're all over it. Why can't 2-methyl-butan 2-ol do it? Well, that's tertiary, isn't it? That's going to be tertiary. How do I know that's tertiary? By looking at it. The methyl group is coming off on the same as the OH, and then it's going to have 2 R groups either side. So if they're putting the alcohol group on as the same as another side group, you're going to have the OH group here, your methyl group there, and they're both coming off the carbon. And then if there's carbons, it can't be done, right? It's going to be tertiary. It's going to have 3 R groups. 2,2-dimethyl-propanol. Yeah. Don't think that can do it. Yeah, it's going to be D. And we can draw it out, but that would be pretty disgusting to draw out. So you go like that. There's that. Oh, yeah. That's a secondary alcohol. Secondary alcohol, because look, it's got a hydrogen coming off of it, and it's got an R group here, and all of this here is an R group. So secondary alcohol. So D is the correct answer. What about the last one? Which alcohol can be oxidized by acidified potassium dichromate but cannot be dehydrated by heating with concentrated sulfuric acid? So, we didn't talk about something that can't be dehydrated. So, which one of these can be oxidized? So, is a secondary or primary alcohol? So, which one of these is a primary or secondary alcohol, but it can't get dehydrated? A, no, B? Yeah, maybe. I don't want to draw these out. It's too painful. Let me make this bigger. I think we're going to finish after this question, so I don't really draw these out, but I'm going to give myself a little bit of white background. That's a little bit easier. Okay, right. Let's do the main chain, butanol. Let's check A out, right? Butan 2-ol. Is this a primary or secondary? It's got to, my first thing is it has to be primary or secondary. So this is 2,3-dimethyl. Oh no. This is a tertiary. Look, it's got 3 R groups. This cannot be oxidized, so it's not A. A is tertiary, thank you. If we go to B, and if you're right, which you probably are, so we're going to go propan 1-ol. So we've got OH. So we're looking at potentially a primary. Let's just see. Oh no, 2,2-dimethyl. So it's got a methyl there. I think you're spot on. I know this is long, guys, but just to explain, this is a primary alcohol. So B is the correct answer. So boom for getting that right, because that was a really good one to get right. So B is the correct answer, and essentially what I want to show you here is why. So it's a primary alcohol. That's because it has only 1 R group. Look at that R group. That is it. Just 1 R group. The others are hydrogens. 1 R group attached to the carbon that has the hydroxyl on it. So it's a primary. Primaries can be oxidized to aldehydes. So that means they're going to change potassium dichromate, the color of it. However, why can't it be dehydrated? Do you remember where the double bond forms? So if I want to snap this off with my hydrogen ion from a catalyst, if I want to snap that off, I'm going to form a double bond here, and there's no hydrogen adjacent. Co-transport in the ilium. Yeah. Yeah, you don't have to draw them out. Like, so, like, what you do is, first off, okay, brass boy, good point, because Nam wants to draw all these disgusting ones out, right? So you would look straight down and you would look for where the alcohol is, and you go, the alcohol is on the second carbon, and there's a methyl on the second carbon. That tells, and it's not at the end, right? It's not 1-ol. It's not 1-methyl 1-ol. It's 2. So that tells me it's a tertiary. So if the alcohol group's in the middle of the chain and something else is coming off of that, that's a tertiary. Cannot be oxidized. Bang. So you don't need to draw it out. This one, let's check the other two. Pentan 3-ol. Pentan 3-ol is a secondary that can be oxidized to a ketone. Why is this not the correct answer? Because it can be dehydrated. What you need to be dehydrated is a carbon atom with a hydrogen on it. So in order to be dehydrated, say my hydroxide's there, the double bond that forms, you have to have a hydrogen here or here to form the double bond. And you're going to get that with pentan 3-ol essentially. There's loads of carbons and hydrogens. So you're really looking for this particular question, you can spot the tertiaries and secondaries just by looking at them. This is propan 2-ol, but it's got a 2-methyl. That's telling me this is a tertiary, cannot be oxidized at all. And then this one is a primary. Generally, if the OH group is at the end, it's going to be a primary. So 1-ol, that's a primary. That can be oxidized. But then what we're looking at is 2,2, next to the alcohol group, there is no hydrogens attached. Yeah, skeletal formula is good, but there's no hydrogens attached here. So because you know that is on, so you go propan 1-ol, right? He says drawing it out to show you. The 2,2-methyl means you've got an R group and an R group and an R group. So this is a primary alcohol, but with respect to where the double bond forms, there is no hydrogen to donate its electrons to form the double bond there. So when you're looking at the dehydration, you want to look at the carbon next to the carbon with the hydroxide group. It's a little bit tricky. It's best to just practice those bad boys. Oh, last one. Very last question before I finish. So which one of these is the correct reflux apparatus for making, no, not reflux, distillation. Is it distillation or reflux? We want to make an aldehyde. I can't really read my screen. Hexan 1-ol to hexanal. No problemos. Yeah, you guys are all over this, man. Well spotted. Hopefully you can, and always a good thing to do, and you'll always come across ones you can't do. That's the nature of it. But a good thing to do. Let me just give you a quick boom for getting that so quickly. Boom! What happened to my boom? It's off screen. Everything's gone pear-shaped. Never mind. It's gone pear-shaped like a pear-bottom pear flask. So this is aldehyde, so yeah, you cross those out because of course they're reflux, and then you do the water in, water out, and this one has got the water in the wrong place. So that's what I'm saying. That's an AQA question. They're testing you on it, and there you go. Well done. Okay, take care guys, and I will see you next time. I'm doing biology on Thursday at 7 o'clock. I can't remember what's in the lead. On the I don't know what's in the lead at the moment for me to go over. I can't remember what it is that I'm going over. Maybe transporting plants. I think I put up transporting plants, transporting insects. So transporting plants like mass transport, sort of phloem, xylem business, cohesion, tension, and the whole companion cell active loading business, I think, might be in the lead at the moment. All right, nice one. Take care, guys, and have a good evening. Keep working hard. A-levels is all about consistent work. If you can work consistently from now till the end, you will do the best that you can do, and then at least you can just pat yourself on the back. You did the best you could do. You know, there we go. All right. Hopefully this doesn't come up half screen, but I'm off. So see you later, guys.
You're still here? It's over.